Right, this section we're going to talk about the conformation of ethane and other hydrocarbons. Hydrocarbons don't exist as flat molecules, or I'm sorry, organic compounds don't exist as flat molecules. They exist in 3 dimensions. And because of that, there's a very specific conformation that these molecules actually adopt. Okay, so we're going to start with ethane and kind of look at ethane, and then we're going to go to butane and look at how these molecules exist. We're also going to do, one of our labs is going to involve this section as well as a section later on in the chapter. Okay, so let's first look at ethane. I'm going to draw the structure. It's called a sawhorse structure. It's a structure where it's trying to show you ethane in the 3-dimensional form. It's kind of, they call it a sawhorse because I guess it looks like, I don't know, a horse or something like that. But it's trying to show you that this carbon is in front, and then you have a bond that goes back, and then you have a carbon in the back. All right, and then you have your hydrogens, one here, and one here, and then in the back you have one that's going up and one that's going to the side and to the side. And then if you have your model set, you might want to make ethane. Your model set will really help. And what we're going to do is rotate around. We're going to rotate the CC sigma bond. Okay, so this bond right here, we're going to imagine I'm grabbing a hold of this carbon. Let's call this carbon 1 and this carbon 2. Imagine I'm grabbing a hold of carbon 1 and I'm rotating it around the CC sigma bond. So what happens is that this, so the hydrogen here stops at this position. This hydrogen here stops position up here, and this hydrogen stops at that position. So what it will look like now is you have a hydrogen that was currently at the top, so the hydrogen right here is now right here. All right. Some people are able to see a lot of this in 3 dimensions. Other people have a hard time at seeing in 3 dimensions. It just depends on who you are. I kind of drew this a little. And then you have an H there, an H there, and an H there. So it's just trying to show you how you just rotate around this bond right here. Okay, and this is what's called a sawhorse. They're not. I think they're very hard to see. So again, some people can see this, some people can't. However, there's another type of way of viewing these, and it's what's called a Newman projection. All right. Right, the Newman projection, I thought I would just write it out to save time. But basically what a Newman projection is that you look down a carbon-carbon bond and compare the spatial relationship between all of the groups. Okay, so it's a different way of viewing these molecules. Okay, so I'll show you what the Newman projection is. So what we're going to be doing is taking ethane again. Let me draw it in the sawhorse fashion again, just to kind of show you how I'm going to be viewing this. And again, if you have your models, it's a lot easier to see. Okay, so let's call this carbon 1 and this carbon 2. All right, this is my carbon-carbon bond right here. All right, because it's a carbon attached to a carbon. That's my carbon-carbon bond. So carbon 1 is going to be in front. All right, you don't really write the carbon. What you just do is you just draw. So notice I have a carbon, and I have the 3 bonds, not the carbon-carbon bond. I have a bond here to hydrogen, another bond here to hydrogen, and another bond here to hydrogen. So notice it's like a trigonal planar form. Okay, so I have the hydrogen on top, the hydrogen to the right, and the hydrogen to the left. And this point right here is our carbon 1. I'm not going to write the carbon. You don't really write it, but if you want to, so that makes sense, that's fine. And what we're basically doing is our eye now, rather than looking at it at an angle, we're actually looking at it directly down this carbon-carbon bond. So my eyeball, I'm going to kind of draw a representation of an eyeball. There's an eyeball. Okay, so imagine I'm looking at it directly at so this carbon and this carbon are right behind each other. So see if you can orient your molecule so that the two carbons, so your top carbon is basically right in front of your carbon 2. Okay, that is what the Newman projection is going to look like. All right, so then in the back, and what they do is they do this circle. And again, you can look in your book. Your book has much better pictures. I think they even have a picture of an eyeball, but they actually have colors. And then this hydrogen right here, this hydrogen is in the back. All right, so you kind of draw it like this. All right, so in a way, this hydrogen and this hydrogen, all right, are eclipsing each other. They're kind of right in front and back of each other. And then this hydrogen right here would be coming out over here, and then the hydrogen right here would be right there. Okay, so that's kind of a representation of this is the Newman projection. All right, now again, if you make your molecule, it might be easier to see it. Okay, but basically these two hydrogens, all right, are eclipsing each other. These technically should be eclipsing, and these two are eclipsing. Okay, and this is what's called the eclipsed conformation. All right, those are the eclipsed. All right, now when we rotate it, so remember like how we saw in the previous page, we rotated it. So now let's say we rotate around the carbon-carbon bond 60 degrees. Okay, so this hydrogen is going to go to here, this hydrogen is going to go to there, and this hydrogen is going to go to there. And we're going to look at the Newman projection. All right, how I draw it is I draw, I guess, a Y, draw it in a Y form. And then you kind of draw this circle, which is in the back. And then the hydrogens in the back stay exactly where they are. Those don't move, just the hydrogens in the front. All right, notice now, the hydrogens are not eclipsing each other. This is called the staggered conformation. Okay? So, and basically you can keep rotating it 60 degrees every time and go from eclipsed to staggered, eclipsed to staggered, eclipsed to staggered. Okay? The staggered is the more stable conformation. Okay, the reason is because you have these interactions when your hydrogens are well, the reason it's more stable is because it's lower energy. Okay. What you have is so it's because your hydrogens are your staggered hydrogens over here are interacting with each other, right? It's called a steric interaction. I'll put it here, steric interaction. All right, so on the eclipsing, so here, let's just put a carbon, and I'll do it on a sawhorse conformation. But your hydrogen has a sphere of electrons, and the other hydrogen has a sphere of electrons, and your electrons have a negative charge. So you kind of have two like charges kind of interacting with each other, and that's a very unfavorable interaction. When you stagger them, you alleviate. So again, I'll do a sawhorse. Now your hydrogen is over here on the side. You no longer have that steric interaction. You don't have that interaction. It's much further away. Okay, so you can see these two are much further away than if you have the two hydrogens over here interacting each other. So that's why the staggered conformation is more stable, lower energy. These molecules prefer to be in staggered conformation. Okay, and because of that, we usually draw the molecules. So I'm going to draw ethane in its full glory. Okay. With all the, so this is a flat version of it. All right, and again, remember that the wedges mean that they're coming out of the plane. The dotted lines means it's going into the plane. Okay, so you have this kind of angled way of drawing the molecules. Okay, remember I drew. So if you draw, let's just say butane, for example, that is butane. If you want to draw it completely staggered, all right, on the flat, this is how technically the molecule really exists. All right, and the reason is because you've alleviated all those steric interactions. Nothing is eclipsing each other. Your hydrogens are at the furthest possible distance away from each other. All right, so you remember I also taught you another way of drawing these, like the skeletal. That's how you draw it, and the reason is because it's showing that staggered interaction. Okay, another one is if we